called small scale fading effect. Let me explain what does it mean small scale, and there is another thing called large scale fading effect that also we will explain. Okay, so let me first briefly tell you about large scale. Suppose here is a base station, okay, and you are moving away from the base station. So now large scale fading effects are prominent when you significantly move. What it means is, suppose you are here with your mobile and you just moved here. So the signal from base station will not appear to be too much, weak. You will not feel any change. But when you will cover large distance, definitely at this point the signal of base station will be weaker, right? I'm just giving you a very layman type of explanation. But small scale fading effects is they are such effects that even if you move by lambda amount, which is the wavelength, and which is very small, even if you move by lambda wavelength, you will feel some fluctuation or change in the signal. Not only that, in case of wireless environment, even if you are stationary, you are not moving, but because of other objects moving, you will feel change in the signal strength. So we will first study the this small scale fading effect, okay, and because this is more important from wireless communication point of view, and then we will also study this large scale fading effect. Now to explain this small scale fading effect, first of all, I will not use, for this part I will not use Rappaport book, and that book is not good for understanding this. Rather, I will use one part of chapter of David Say. Okay, we don't need to go through the book, you just go through my videos, but for sake of yourself, I can share you the PDF of that part of chapter, okay, with you, no issues, which you need. But if you just attend my video, that is sufficient. Now we will take first of all a case of free space. Okay, free space means you are communicating just like a satellite communication. Okay, so there is nothing in between. Then you have fixed transmitting antenna and receive antenna. Okay, now how will the field appear? You know that what we transmit via antenna is the sinusoidal wave, right? So if at the source, if you transmitted cos of 2 pi ft, where f will be the definitely carrier frequency, so this is the source, right? See, I'm not writing an amplitude and other things, I'm just writing one part. Just if you recall your AM or FM or even BPSK or QPSK, okay, so in addition to this amplitude part, so there is this main part is the cosine signal, right, or the sine signal. So that is what is transmitted. Then what will be when you transmit at the antenna? So at distance r and time t, okay, what will be the response at distance r? So I will write that response in terms of electric field. See, here's one fact. First of all, in free space the power is decreasing as 1 over r square. Hence electric field, if you people know the relationship between power and electric field, will decrease as 1 by r, right? You see, electric field is related to voltage and power is proportional to voltage square. So hence electric field has to decrease by 1 by r. Now at time t you transmit this signal. So here is the source, you transmit signal. So at distance r, and this r is far from antenna. This is important. You might have studied in antenna theory. Then the field pattern near the antenna is very complicated. But as we move away from the antenna, something called far field, that is well understood and has a good mathematical structure. So when we go far, so how will the signal appear? So cos of 2 pi f. Now the signal has covered the r length. So hence the time taken for signal from antenna to this point is r by c. C is the speed of light. So it will be t minus r by c, right? And divided by r, there will be a constant. I will call that alpha. This constant depends upon radiation pattern. Radiation pattern of antenna. So you don't worry about its understanding because we will not need it later on. This is not. It may depend upon. There are some parameters, azimuthal angle and other, direction angle and frequency. So this comes from antenna theory. So for us, it is just a constant. Okay, nothing else. So this I can represent as electric field. So hence electric field at frequency f at time t, and three parameters r, theta and psi. These are the three parameters for pattern, is equal to some pattern constant which depends on theta, psi and f, cos of 2 pi f t minus r by c divided by r. Okay. So we are not here concerned about finding the radiation pattern. That I will repeat it only again, so that you don't really become confused about it. Okay. Now this was a transmitted antenna. Now suppose at distance r you have a received antenna. Okay. So how will the received antenna signal? How will he receive the signal? I will write that as ER, again function of ft, and let me call this as u. R theta psi as u. So it will have its own radiation pattern. I will call it alpha. Again, we are not concerned about that. The main thing is change in the cosine signal, cos 2 pi f t minus r by c divided by r. So you can say that its pattern is almost same. Okay. Now here is one, you can see a remarkable thing we can think about it. You can treat, see this transmit antenna, receive antenna, and the space in between. You can treat it as a system. Okay, as if you have a system and you transmitted some signal, right, E, and you received a signal ER with this electric field, and you have some particular transfer function also for this. So we can represent wireless system as linear time invariant system. Okay, that is one, you can say, a remarkable thing, because it will really simplify things later on. Okay, we'll come back to this again when we will try to model the channel. Now this was a very simple setup. Now let's take scenario, very first wireless or practical mobile scenario. We are in free space, but we have a moving antenna. Antenna is moving. So in this scenario, we have a received antenna. So here is a transmit antenna. Okay. But receive antenna, suppose it is moving with velocity v. You are with a mobile and you are moving with velocity v. Okay. Then this distance from this antenna will now be function of time, right? Okay, let's say that initially it was at distance r0, and then it started moving with velocity v. So at time t, the distance from will be r naught plus bt. So at time t is equal to 0, r of 0 is r naught. It was initially at r naught and then it started moving, right? So then what will be the electric field? So it will be function of f, of course now t, but it will be now function of r naught plus bt also. I don't care about now antenna. So here is alpha s, some pattern constant, cos of 2 pi f t minus r naught plus bt by c, right? Divided by, instead of r, again it will be now r naught plus bt. See, we are basically main worried about these changes in denominator as well as the changes in this phase, right? This is very simple. Now the inside thing of f of t minus r naught by c plus vt by c, we can also write it as f of 1 minus v by ct, right, by taking this t as comma, minus then f r naught by c. So what has happened is that if you see at this part, it looks like the frequency was actually f, but now there is a shift in frequency by amount minus f v by c, and this we call as Doppler shift, and this has happened because of the motion of the receiver, right? Now let's take another scenario, that is of reflecting wall but fixed antenna. Okay, in that you have, suppose here, transmit antenna, and here is a wall. This distance is d, right? And you are here, suppose you are stationary, not moving, and you are at a distance from this transmitter. But now you are not only getting the incident wave from this side, you are also getting the reflected wave also. What will be the effect of this wall? What will be the effect of this reflection? Okay, so very simple. Reflection changes the phase. So at the receiver, your electric field can be written as alpha. So one is cos. So one part is directly at distance r, cos of 2 pi f t minus r by c divided by r. Nice. And the second part will be minus alpha, because there is a 180-degree phase shift. So minus alpha cos 2 pi f t minus. Now you have to see how much distance has been covered. So this signal which comes from this point and then here, how much distance covers? This is d plus how much is this? This is d minus r. So d plus d minus r, which is 2d minus r. So it should be 2d minus r by c divided by 2d minus r. Very simple. There is nothing big. I am just using basic mathematics and basic physics here. Now the receiver receives something called superposition of two waves. Superposition of two waves, both at frequency f. What is the phase difference between the two? Phase difference is, so what is the phase of second part? It is 2 pi f 2d minus r by c. Now while computing the phase difference, I will do one thing. I will write here plus, and I will write plus pi inside. That is more okay. Okay, this is plus pi, this is better. This is the phase of this term minus phase of first term 2 pi f r by c. This I will represent as delta of theta. Okay, so how much will be this? Just compute. It will become 4 pi f by c d minus r plus pi. We know that if this phase difference is an integer multiple of 2 pi, then what will happen? Constructive interference will happen. Similarly, if it is odd multiple, suppose 2n minus 1 of pi, then destructive interference will happen. Right? So now here is, although it is not moving, but as a function of r, if you change this r, this receiver will receive, a special pattern of constructive and destructive interference of the waves. So if you move, suppose now, if you change the r, you will get sometimes peak, sometimes valley, right? So what will be this peak to valley distance? Okay, so initially this is your transmitter, right? So your r was first here, and then r is here. At this r, the phase change was integer multiple of 2 pi. You got constructive interference, and here you got destructive interference. Now this distance is called distance between these 2 points, where you move from a constructive to destructive interference. This is called coherent distance. Okay, and is denoted by delta xc, and it can be easily derived, right? So when delta theta is suppose 2 pi, right? So let's write 4 pi f by d minus, let's say r1 is distance at that point, plus pi is 2 pi. Then you have 4 pi f divided by c d minus r2 plus pi is equal to pi. So this part is constructive part. This is the phase when it is constructive, and this is for destructive, right? So now if you subtract the two, what will you get? So first of all, 4 pi d by c minus r1 4 pi f by c plus pi minus 4 pi f by c d plus 4 pi f r2 by c and minus pi is equal to 2 pi minus pi. I'm doing it very simply. So pi gets cancelled, 4 pi dfc, 4 pi dfc gets cancelled. So I have r2 minus r1 times 4 pi f by c is equal to pi. So this pi and pi also goes. So r2 minus r1 is this is called coherent distance, delta xc times is equal to c divided by 4f. C by f is lambda, so lambda by 4. So delta xc is lambda by 4. See, this is small scale effect, right? It means that if you change r just by 1/4 of wavelength, you will at one point you will get the constructive interference, you will get the maximum signal. At other point you will get destructive interference. This is the small scale fading effect. Okay, I will continue with this discussion. After that we will do when there is a reflecting wall and antenna is moving also with some speed v, what will happen. So these small models will prepare us for a large picture of small scale fading. And finally I will show you briefly how to use statistical modeling, probabilistic modeling for small scale effects and how to model the wireless channel. Okay, thank you for this.